In this video, we want to prove a very interesting and important property of parabolic mirrors, which is that they converge a parallel beam of light to a single point. There are many ways to go about showing this. One of them is the method which is widely used in physics, which is Fermat's principle, which tells us that light always takes the path that requires the minimum travel time between 2 points A and B. The second method, which is the one we are going to look at here, is kind of purely based on geometry. So we just want to use the laws of reflection in this case, and some mathematical notions like functions and tangents and angles and all of that. So affine geometry somehow to show that any ray of light that hits this parabolic mirror is going to be reflected to the point F, which is the focal point. In this case, we know that the general equation of a parabola is y minus k squared equals to 4p x minus h, all that squared, where in this case, hk, which is the center of the parabola, we place them at 0 in order to kind of simplify the problem. In this case, p, which is f, should just be 1 over 4. So the distance between O and F is 1/4. So this is also equals to p, this p. So that's what we want to show in this case, in this little exercise, in this little tutorial. To go about this, the idea here is to calculate the equation, the Cartesian equation of the reflected ray. As you can see here, this is R. Here we have the incident ray. It's reflected at the point P, which in this case we suppose has coordinates A and B, and then it should go to this point F. So if we are able to calculate the Cartesian equation of this reflected ray, what I call here R, then we would simply need to calculate its intercept at the origin, and that should give us 1/4. So that's what we want to do here. So as a prerequisite, you probably know that the gradient of a function at a point is given by the derivative of the function at that point. So in this case, we are having the point P, which has coordinates, let's call them A and B. So what we can do here already as a first step is to calculate the gradient of the tangent and the normal using that simple notion of it's an application of differentiation. The gradient of a curve at a point, which is also the gradient of the tangent, is just the first derivative of the curve at that point. So we can say that the gradient, or call it m, of the tangent t is just the first derivative of x at the point P. So in this case, the point P has an x coordinate of a, so it's f prime of a. And that's just 2a, because you just differentiate that. The gradient of the normal is just -1 over the gradient of the tangent. So that's just notions of geometry. And this is just -1 over 2a. Also, this horizontal line that passes through the point P at the point of incidence, it's a horizontal line, so it has a gradient of 0. So we are going to make use of these three parameters. So we want to look for R. Let's call its equation R of x. We know that the equation of a straight line is of the form px plus q. Okay, where p is the gradient and q is just the y-intercept, which is what we are looking for in this case. So if we want to get the equation of R, we first need to know its gradient or its slope. And to look for that slope, we are just going to use a simple trick. The first thing we can consider here is the angle between the reflected ray and the normal. Okay, we can establish a relationship between the gradient, the slope of this normal, and the slope of this reflected ray, which is what interests us here. In this case, we know the angle between these two. As you can see, this angle is just going to be equal to this angle, which is theta. So knowing the angle between these two lines, we can establish a relationship between their slopes. So tangent of theta is just going to be the difference between the slopes. So m of r minus m of n divided by 1 plus m of r times m of n. So this formula is just the tangent of the angle between two lines as a function of their slopes. So this gives us m of r plus 1 over 2a divided by 1 minus m of r times 1 over 2e. Okay? So the only unknown, well, the unknowns in this equation are m of r, so this, and tan of theta. These are the unknowns. So we'll try to look for tan of theta, and having tan theta, we'll be able to get m of r. To get tan theta, we use another trick. This time we are going to consider the angle between h and n. So the angle between these two lines. We can do that in this case because we know the slope of n, the slope of h. So we can also express the tangent of the angle between the two. In this case, it's this angle. And you can clearly notice that this angle is just going to be equals to 90 minus theta. Because if he is theta, this is a right angle, so he is 90 minus theta. And since these two angles are opposite, this one is also 90 minus theta. So we can also write that. Let's call this point. Let's call this point 1. Let's call this point 2. So we can also write that tangent of 90 minus theta. Okay? Again, we apply the same relation for these guys. It's going to be the gradient of the horizontal line, which is 0, minus the gradient of the normal, which is mn, divided by 1 plus the product of the two slopes. So that's just negative mn. You recall probably from your trigonometry class that the tangent of 90 minus theta is just 1 all over the tangent of theta. So this would be equals to negative mn. Okay, but mn, we know its value. It's negative 1 over 2a. So this implies that 1 all over tangent of theta is equals to negative 1 over 2a, giving us tan theta as, so that's minus of minus, so giving us tan theta as 2a. So this is the first important point that we can note here. So we have the tangent of theta, okay? We can replace it here and get m of r. So I'm going to change paper so that it should not be too squeezed into one place. So let's write that here. We have tan of theta, which is m of r plus 1 over 2a divided by 1 minus m of r times 1 over 2a. And this should be 2a. So equating this to this. So we can solve for mr here. We have mr plus 1 over 2a equals to 2a times 1 minus mr times 1 over 2a. So if we simplify this, we are going to get mr as a minus 1 over 4a. So this is the slope of that line. Let's box that. So having this slope, we can then proceed to get now the equation of r of x. So calculating r of x. R of x here is just the Cartesian equation of this reflected ray. You recall that the general equation of a straight line is given by y minus y0 equals to m times x minus x0. So m is just the slope, and x0, y0 is just a point through which that line passes. In this case, our x0, y0 is the point P, which has coordinates a and b. So it's this point P. So we can do that. We have y minus b equals to a minus 1 over 4a, okay, times x minus a. So this gives us y equals to a minus 1 over 4a times x minus a plus b. Okay, but then we can also express b in terms of a, because b is just f of a. And if you recall, f of x was just x squared, so f of a is a squared. So we can have this. So overall, we're going to have y as a minus 1 over 4a times x minus a plus a squared. So this is r of x, if you want, is the Cartesian equation of that reflected ray. So I'm just going to put it in a box. So having this, we can now proceed to calculate the y-intercept of this equation, which should correspond to the focal point. And let's do that and see if it gives us the result we expect. So when x is 0, let's calculate the value of y. So y is going to be a minus 1 over 4a times 0 minus a plus a squared. So that's just, so that's a squared, that's minus a squared, then plus 1 over 4, this times that, plus a squared. So this term cancels with this one, and that gives us 1 over 4. So we effectively get the result we expected. Y is equals to 1 over 4. And this corresponds to the focal point, F. So this result is very interesting and very powerful, because it tells us that whatever the incident ray that you want to take, okay, once it hits the surface of this parabola, it's going to converge, it's going to be reflected to the focal point. All the rays, so far they are parallel to this y-axis, they will all converge to the focal point. And only a parabolic surface can enable us to achieve that. And that's a very important property of parabolic mirrors, which are made use of in astronomy, in telescope designs, and many more. So I hope you find this interesting. Okay, if you are also interested in the derivation of this result using Fermat's principle, because we can do that using Fermat's principle, as I earlier mentioned, just let me know in the comments, and I'm going to make another video on that one. It's actually way shorter than this one. It's just a few lines, that's just one page. But yeah, so hope you find this video interesting and that you like the geometry. Let me know if you had already encountered this derivation before. If not, add your opinion about that in the comments. And then I see you in the next video to talk about another interesting topic. Until then, remember that physics is the belief that a simple and consistent description of nature is possible.